Hello and welcome. Today, we're going to talk about frequency synthesizers. What are they? Why are they important? And what you need to know about them. Look around you. Every piece of technology you encounter contains some kind of frequency generator. Now, if you're a computer engineer, you call this a clock. Not like a kitchen clock or a bedroom clock. It's not there to tell the time. Instead, it's more like a metronome, keeping a steady rhythm, like an orchestra conductor keeps all the musicians playing at exactly the right tempo. In a computer, everything has to be precisely timed so that data arrives where it's needed, exactly when it's needed. But if you're a radio engineer, you probably call the frequency generator an oscillator. A radio transmitter uses an oscillator to generate a pure sine wave called a carrier, precisely on the transmit frequency, and then uses a modulator to impress the information to be transmitted onto the carrier. In the receiver, a signal from a local oscillator can be mixed with the received signal to help recover the information that was impressed onto the carrier. These oscillators have to be precise to ensure that you're transmitting on the right channel and not interfering with other users. But having a fixed frequency generator just isn't enough. Most of the time, you need some kind of frequency generator that can change frequencies easily. Don't believe me? Well, think about two common applications. First, in your car you probably have a radio, and unless you're driving an antique, that radio has some buttons and a digital display for the frequency. Well, how does that work? The answer is that there's an agile frequency generator inside that forms the local oscillator that we just talked about. The frequency generator can be configured to produce a wide range of frequencies, each frequency corresponding to a channel on the AM or FM bands. If you had only a fixed frequency generator, you could only receive one station. Boring! The other application is probably right in your pocket, your mobile phone. Hey, have you ever stopped to consider just how many radios are in a common cell phone? There's at least one for the cellular function, another one for Wi-Fi, and yet another one for Bluetooth, and still another one for near-field communication. Hey, that's a lot of radio transceivers in there, and every one of those transceivers has to be frequency agile. The Bluetooth radio alone has to tune to one of 79 channels. Well, that's why it's not enough just to have a frequency generator. You need a frequency synthesizer. Now, first off, what's in a frequency synthesizer? Well, at its core, there are two blocks. First, a precise, stable oscillator to provide the master clock, and a block called an M/N divider. It's this latter block where all the fun stuff happens. That block contains the magic that converts a fixed input frequency to a nearly infinite array of output frequencies. And we'll get back to that block in due course, but first we really need to talk about that first block, the master oscillator. Now think about it for just a moment. How would you generate an accurate, consistent, stable frequency? Well, the good news is you don't have to think about it very hard. Engineers have been creating oscillators from electronic components for more than a century, so we have a pretty good handle on how that works. Let's start with something simple, a relaxation oscillator based on a Schmidt-Trigger inverter. Now, the oscillator is simple. It needs just a resistor and a capacitor in addition to the inverter. Now, it works like this. If the capacitor is discharged, then the input is near 0 volts. The inverter output is in a 1 state, so the capacitor begins charging through the resistor. When the voltage on the capacitor exceeds the inverter's upper threshold, the output switches and goes low. Now the capacitor begins to discharge through the resistor until the voltage on the capacitor falls below the inverter's lower threshold, at which time the output switches back to a 1 state, and so on. Now, this kind of oscillator has a lot going for it. First, it's really reliable. It's guaranteed to start and run every time. And it's easy to understand. The output frequency is a factor of the resistor, the capacitor, and the threshold voltages of the inverter. Now, the problem is that all capacitors drift in value with temperature and age. And even if you could get a capacitor that was perfectly stable with temperature and time, getting a capacitor with a value precise to a fraction of a percent is extremely expensive. So, while this oscillator works great for some applications, it's not really suitable for a precision timing reference. Now, there are other oscillators based on resistor-capacitor timing, like the astable multivibrator shown here, and it also emits a square wave. And then there's also the phase shift oscillator, and unlike the relaxation oscillator or the astable multivibrator, the phase shift oscillator produces a sine wave. But all of these oscillators still have that problem. While they're reliable, they're not frequency stable. Well, fortunately, there is an easy way to make a frequency-stable oscillator, and that's with a quartz crystal. This circuit is called a Pierce oscillator, and it's the most commonly used crystal oscillator. But what's so special about a crystal? Crystals work on the principle of piezoelectricity. That's the property of some materials, including quartz, to generate an electrical potential when they're stressed, and to flex slightly when an electrical potential is applied to them. Now here's the thing. When you apply an electrical pulse to a crystal, it doesn't just flex and relax. It flexes, and then it swings back and forth like a guitar string. And all the while it's swinging back and forth, it's creating an oscillating electrical potential at exactly the frequency of its swinging. Now, you can amplify that signal, apply some phase shift, that's what the inverter does, and feed it back to the crystal, and in that way, you keep the signal going. Cool, huh? But sad to say, not all crystal oscillators are created equal, and that's important because the better the reference oscillator, the better the overall signal quality of the frequency synthesizer. But what do we mean by better? Well, ideally, the reference signal would be a sine wave of constant frequency, never varying in frequency, phase, or amplitude. Now, in the real world, such perfection is practically unobtainable, but we define how close we come to the ideal using engineering principles. Now, if we consider the amplitude of the signal produced by the oscillator at its primary operating frequency as 0 dB, and then measure the noise power in a 1 Hertz wide slice at some frequency offset away from the primary operating frequency, we can estimate the quality of the oscillator. The lower that noise power, the better the oscillator. Now, the spectrum analyzer plot that you see superimposes two 1 GHz signal sources. The horizontal scale is zoomed into 1 kHz per division, and the vertical scale is 10 decibels per division, with 0 dBm at the top of the screen. Now, notice, the signal source represented by the blue trace is down 50 dB at 1 kHz offset. But the pink trace is down about 65 dB. Well, that means the signal source represented by the pink trace has significantly better noise performance than the signal source represented by the blue trace. The parameter you should look for when evaluating signal sources is dBc per hertz. dBc stands for decibels referenced to the carrier level. That is, if you consider the output level at the main oscillator frequency as 0 dB, then measure the level at some offset, the ratio can be expressed as dBc. Consider the power integrated over a 1 Hertz bandwidth around some offset, and that's dBc per hertz. Frequently, you'll see the performance specified at a 100 kHz offset. If you have a clock source with a noise margin of minus 130 dBc per hertz at a 100 kHz offset, then you have a good clock that's probably sourced from a crystal oscillator. Now that we have a stable oscillator, let's crack open that M over N divider. Now, the first thing to recognize is that M and N are both integers. That is, at its core, we're multiplying the input frequency by one integer factor and dividing the frequency by another integer factor, and not necessarily in that order. Since dividing a frequency is simpler than multiplying a frequency, we'll start there. Let's begin with the basics, a JK flip-flop. Now, a JK flip-flop is a basic logic circuit that has a clock input, two logic inputs labeled J and K, and two complementary outputs, Q and Q bar. A JK flip-flop works like this. If both the J and the K inputs are 0, the flip-flop holds its state. It doesn't change when the clock ticks. If the J input is high and the K input is low, the flip-flop is unconditionally set when the clock ticks. That is, the Q output is driven high and the Q bar output is driven low. And similarly, if the J input is low and the K input is high when the clock ticks, the flip-flop is unconditionally cleared. The Q output is driven low and the Q bar output is driven high. Okay, so far, so good. But what if both the J and the K inputs are high? Then, each time the clock ticks, the flip-flop changes its state. In the language of the designer, it toggles. If the flip-flop was set, it becomes clear. If it was clear, it becomes set. Now, we can use this behavior to cascade several flip-flops from the Q bar output to the clock input to easily build a circuit that can divide an input frequency by any power of 2. The circuit shown here is called a ripple counter, and that's because the count ripples through the various stages. Flip-flop 1 depends on flip-flop 0, flip-flop 2 depends on flip-flop 1, and so on. In this circuit, the Q output of flip-flop 2 will be driven at 1/8 the frequency of the input clock. A ripple counter is easy, cheap, and as long as the propagation delay of the flip-flop is small compared to the period of the clock, extremely reliable. Now, that covers division by even powers of 2, 2, 4, 8, 16, and so on, but what about division by integers that aren't powers of 2? Well, it turns out that's pretty easy as well, and there are multiple ways of implementing a divide by n counter, where n is some arbitrary integer. Now, I'm not going to go into the details about how to build a generic divide by n counter, but if you're interested in following up, do a quick search for synchronous counter. There are lots of resources out there that merit your study. So that's how you divide an input frequency by any integer you like. You can take a 10 megahertz signal and create a 5 megahertz signal, a 3.33 megahertz signal, a 2.5 megahertz signal, a 2 megahertz signal, just by dividing by 2, 3, 4, or 5. Or you can do any other integer division you want to consider. But what about frequency multiplication? Well, to understand that, we're going to have to take a little detour. And that detour leads us to the phase-locked loop. That's a bit of a mouthful, so engineers have shortened this to just PLL. The PLL is one of the fundamental building blocks of modern RF technology, and so we're going to spend a little time so we can really understand it. This is a basic phase-locked loop. Every PLL contains 3 main blocks: a phase detector, a low-pass analog filter, and a voltage-controlled oscillator. And that's it. I mean, it looks pretty simple, but there's actually a lot going on here. Now, to start, let's assume that the input frequency and the VCO frequency are the same, and that the two signals are in phase. Now, in that case, the phase detector sees 2 in-phase signals, so its output is 0. Feed a 0 value to a low-pass filter, and you'll get a 0 output. That 0 output is passed to the VCO input, so the VCO doesn't change its output frequency. The loop is stable, and in this condition the loop is said to be locked. You'll see why in just a moment. Okay, now let's say that the input frequency begins to drift higher. The phase detector will begin generating positive pulses toward the low-pass filter. The filter will smooth and average these pulses to a rippling positive DC level, forcing the VCO to run faster until the input frequency and the VCO are once again in phase at the same frequency. The system is still stable, and the loop can still be said to be locked. Now consider the case where the input frequency begins to fall. Now the phase detector begins generating negative pulses that are rectified by the loop filter to create a negative DC level. That forces the VCO to run more slowly until, once again, the input frequency and the VCO are in phase and matched in frequency. Now the system is still stable, and the loop is still locked. And really the only way the loop becomes unlocked is if the input frequency varies too quickly or by too great an amount for the loop filter and the VCO to keep up. In such a case, the loop is said to be unlocked, but it will lock again when the input frequency returns to the lock range of the loop. Now, one common use for phase lock loops is for an FM demodulator. Now think about it this way. If you apply a frequency modulated signal to the input, the phase detector and loop filter will try to push the VCO to track the input signal, and as a result, the amplitude of the output of the loop filter will track the input frequency and present a pretty good representation of the modulation waveform. This technique is currently the most commonly used method to demodulate FM signals in modern receivers. Yeah, but we're not putting an FM signal into the phase-locked loop. We're putting in a pure, constant frequency. So what will we get at the VCO output? Well, we'll get a pure, constant frequency. So what's the point? Well, the point is in the feedback loop. What if we put one of our frequency dividers that we just learned about into the feedback loop? Now we can start with something simple, let's say a divide by 2 block. Now if you add a divider block, the phase detector will sense that the loop is unlocked and it will try to push up the VCO frequency so that the input frequency and the feedback frequency are the same. But to do that, it has to push the VCO frequency so it's running twice as fast as the input clock because of the divide by 2 in the feedback loop. And when it finally does get back into lock, the PLL will be generating a nice, clean, stable signal at twice the input frequency. Okay, at this point in the discussion, we actually have all the pieces we need to build a frequency synthesizer, but before we go on, I just want to spend a little more time thinking about the PLL. Here's a little more detailed diagram of what goes on inside a phase lock loop. First, let's talk about the phase detector. Now, not all phase detectors generate 0 volts at 0 phase difference. Now in this case, the phase detector produces a 50% duty cycle waveform when the divided VCO frequency and the crystal oscillator have the same frequency but are exactly 90 degrees out of phase. When the VCO runs faster than the crystal oscillator, the phase detector produces a duty cycle less than 50%, which slows down the VCO, which keeps the two signals exactly 90 degrees out of phase. And when the VCO runs more slowly than the crystal oscillator, the phase detector senses the change and produces a duty cycle greater than 50%, and that speeds up the VCO. And once again, the two signals stay exactly 90 degrees out of phase. Now, for a lot of PLL designs, this makes a lot more sense than a true bipolar design with 0 phase shift. The loop filter and the gain block smooth the pulse train to create an average DC level. At a 50% duty cycle, the average DC level should be exactly 1/2 the full range voltage, and a smaller or larger duty cycle causes the DC level presented to the VCO to rise and fall as well. Now, assuming the VCO has a wide enough range, increasing the frequency divider's divide ratio will make the VCO output frequency increase. Put in a 1 MHz crystal, set the divide ratio to 10, and you'll get a 10 MHz output. Now here's an example of a really simple phase detector, an exclusive OR gate. Now, exclusive OR is one of the fundamental logic operations. When both inputs are 0, or when both inputs are 1, the output of the gate is 0. But when the inputs are different, the output of the gate is 1. In this example, we assume that the XOR gate has inputs that sense and switch to 0 when the input signal goes below ground, and switch to 1 when the signal goes above ground. And that means that the gate sees the input sine wave as though it's a square wave with transition points where the sine wave crosses ground. Now, if we're using an exclusive OR gate as a phase detector, we need to design the loop so that a 50% duty cycle is seen as a locked loop. That means the output of the VCO will be out of phase with the input signal by exactly 90 degrees. The exclusive OR gate is an inexpensive and common phase detector used in phase lock loops. Well, here's another phase detector that uses current sources to charge and discharge the capacitor in the loop filter. In the phase detector block, the reference frequency is applied to the R input, and the output of the VCO, divided as appropriate, is applied to the V input. The U and D outputs drive the frequency of the VCO up and down, respectively. Switches S1 and S2 are never on together. S1 charges the capacitor in the loop filter, and S2 discharges the capacitor in the loop filter with a time constant set by the current source and the value of the capacitor. Now, in this design, the output of the phase detector isn't swinging from VDD to ground and back. It's just adding or removing charge from the loop filter capacitor, so the signal to the VCO requires much less aggressive filtering. Now, these are just two examples of how to detect phase in a PLL circuit, and there are many others. If you're interested, there are lots of online resources that document many more phase detector designs. But for now, let's turn our attention to the VCO. There are lots of ways to build a voltage-controlled oscillator, but this one is tried and true. Now, Q1 is a unijunction transistor. A UJT has a single p-n junction at the emitter. Because of the way the UJT is constructed, the emitter base 1 circuit exhibits negative resistance, so as C1 charges through R1, the emitter pin does not conduct until, at a certain threshold, it suddenly does, dumping all the charge on C1 through R3. Then the UJT turns off and goes back to blocking until C1 charges sufficiently again. Now, the frequency of this charge dump cycle is dependent on how fast C1 charges, and that's dependent on the value of C1, the value of R1, and the voltage applied at Vn. So the higher that applied voltage, the higher the frequency, and Q2 is a simple emitter follower circuit that provides current gain for the output. Okay, one might imagine that at this point, we have everything we need to build a frequency synthesizer after all. We know how to build an integer frequency divider. We have a couple of different phase detector designs. Averaging filters are a dime a dozen. And we've seen at least one voltage-controlled oscillator design, and since we learned the trick of putting a frequency divider in the PLL feedback loop, we know how to multiply frequency by an integer. Great! Now we're ready to design the M/N frequency synthesizer we want. Well, not so fast. There are still two problems to resolve, and they both relate to speed. One concerns things happening too fast, and the other concerns things happening too slowly. Let's begin with the too fast part of this, with a question. What output frequency do you want? Now, before you answer, think about this. You may be designing a frequency-agile Wi-Fi radio or a Bluetooth radio, and both of these standards operate in the 2.4 GHz ISM band. And Wi-Fi can operate in the 5 GHz ISM band. And hey, radios for the 5G cell standard are going to operate above 25 GHz. That means you'll probably have a need for a frequency synthesizer that can produce frequencies well north of 1 GHz. Building a VCO that can run that fast isn't the problem, but here is the problem. Even as we hear about microprocessors with multi-gigahertz clock speeds, most high-speed CMOS logic families top out at a few hundred megahertz max. But if I want to synthesize frequencies in the gigahertz range, I have to find a frequency divider for the feedback section of the PLL that can divide frequencies up in the gigahertz range. Tricky. Well, not really. The trick is that we build a divider that starts off with a prescaler. Now, a prescaler is a specialized block that most frequently uses a bipolar logic family that can run at the gigahertz rates we want. The prescaler typically works with a fixed divider and usually is just a few stages, often between 3 and 8 divided by 2 flip-flops, to give a prescaler divide ratio of 8 to 256. So for example, if the PLL is expected to generate a signal in the 2.4 GHz ISM band, one might divide by 16 to present a 150 MHz signal to the input of the programmable divider. Then the programmable divider can further divide the VCO frequency to match the reference oscillator frequency. So using this technique, the designer can free themselves from the speed limitations of their chosen logic technology and manage much higher frequency output signals. Okay, so that's how we fix the too fast piece of the equation, but there's also a too slow part. What's that? If we put the N part of the M over N synthesizer between the oscillator and the phase detector, the input to the phase detector will be slower than the reference oscillator by a factor of N. If N is small, that's not a problem, but if N is large, so that the reference frequency is comparatively small, well, we can run into problems. Why? Because if the output frequency from the phase detector is low, then the loop filter, and remember, that's an averaging filter, has to be slow. And that, in turn, means that the loop settling time is going to be slow, and bigger capacitors have to be larger, and size matters in this thinner is better world. But you know, there's another factor that isn't so obvious. Multiplying the frequency in the PLL also multiplies the phase noise. If you're looking for a clean output, you want to minimize the overall multiplication factor, which means you also need to minimize the divider. Well, since large values of N appear to be problematic, let's just use small values of N. But see, that's a problem too. The larger the value of N, the smaller the resolution of the synthesizer. Now think about it. Let's say you're building a receiver to tune the AM broadcast band. That means you'll need a step resolution of 9 kHz or 10 kHz, depending on the part of the world we're designing for. In fact, you may want to make your receiver switchable from 9 kHz channels to 10 kHz channels. So you might decide the best option is to have a step resolution of 1 kHz. But that means your reference frequency has to be 1 kHz or a submultiple of 1 kHz. So to synthesize a 1 MHz output signal, you got to multiply by 1,000, and we're back to the problems associated with a large value of N. An ideal solution would be if we could put a block into the feedback loop that could divide by fractional values. If only... Well, as it turns out, dividing by a fraction isn't all that difficult. It's clever, but it's not difficult. Now the catch is, when you construct a non-integer frequency divider, the output of the divider isn't a nice square wave. Instead, the output of the fractional divider stage will switch between two values that are separated by 1. Now the good news is, if N is reasonably large, the difference between N and N plus 1 isn't much. So the output looks almost like a square wave. Let's take a look at the diagram. The divider stage wants to divide the VCO output by the non-integer value, 25.6. Now one way to make that happen would be to divide by 25 for 40% of the time, and by 26 for 60% of the time. The output of the phase detector will see jitter on that input. But hey, that's why we have an averaging filter at the output of the phase detector. It averages out the jitter, and the DC value to the VCO is exactly the value we need to push the loop to the right frequency. Now, think about the benefits. The reference frequency, that is, the crystal oscillator frequency divided by the input divider, can be higher, since the resolution of the smallest frequency step is no longer totally dependent on the input reference frequency. Now, the fractional N divider can take up some of that slack. And, we're going to need a little math, but hey, we have a big, strong microcontroller to handle that. With the reference frequency higher, the loop divider can be smaller, and that's better for phase noise. Remember, the phase noise in the PLL output was directly related to the divide ratio in the loop. And with a higher reference frequency comes smaller components in the loop filter as well. We also get better settling time and faster lock time. Wow, it sounds like a fractional N divider ticks all the boxes. But how do we actually build one of these things? Well, here's one example of a fractional N divider that's based on an overflow accumulator. Now, there are lots of ways to build a fractional N divider, but this is one of the clearest. First, let's define the players. At the top is the N register. It holds the integer part of the fractional N divider. The N register can be used directly, or on a second path, it can be incremented by 1. Now, remember how in the previous slide, when we wanted to divide by 25.6, we said sometimes we want to divide by 25 and sometimes we'll divide by 26? Well, here we are. The N value and the N plus 1 value go to the inputs of a 2-input multiplexer. Now, when the multiplexer is in the 0 state, the N value is gated to the reload input of a down counter. But when the multiplexer is in the 1 state, the N plus 1 value is gated to the down counter's reload input. The down counter automatically reloads every time it counts down to 0. But what selects which multiplexer input will be used to reload the counter? Well, that's where the overflow accumulator comes in. Every time there's a rising edge on the clock to the phase detector, we get to select a new reload source, either the N or the N plus 1 value. We make that decision by adding a constant, k, to the previous value of the accumulator. The k value determines the fractional part of the fractional N divider. Now, if the addition operation results in an overflow, then the multiplexer selects the N plus 1 reload value. But if the result doesn't overflow, then the multiplexer selects N as the reload value. Okay, I think an example is in order. Let's assume that the F register, the adder, and the K register are all 3 bits wide, and assume that the F register starts with a value of 0, and that we load 5 into the K register. To start, N is the preloaded value, and the counter counts down from N to 0. After N clock cycles from the VCO, the clock occurs toward the phase detector, and the F register is also clocked. Now, because K is 5 and F is 0, the adder produces the value 5, and that's what gets clocked into the F register. But notice this, immediately, because the adder is completely combinatorial, both inputs of the adder contain the value 5, and 5 plus 5 is 10. But for this example, we have only a 3-bit adder. Instead of 10, the output becomes 2, and overflow is set. With overflow set, N plus 1 is selected as the reload value. The next time the clock to the phase detector fires, the F register gets 2. That's the value at the output of the adder. K is still 5, and the sum is now 7. So this time, the overflow bit is clear, and N is once again selected as the reload value. And so it goes clock by clock, selecting either N or N plus 1 as the reload source each time the phase detector clock fires. Now, consider, with our 3-bit adder and 3-bit registers, there are only 8 possible states. The value of K determines how many of those states will produce an overflow. In our example, 5 of the 8 states, whenever the F register is 3, 4, 5, 6, or 7, will cause the overflow bit to become active. And that means, on average, the fractional N divider will divide by N plus K divided by the number of possible states of the F register. In our example, that means N plus K over 8. Another way to think about it is that the fractional part is K divided by 2 raised to the power of the number of bits in the register. In our example, the fractional part is K over 2 to the 3. So if N is 25 and K is 5, the output frequency would be 25 and 5/8 times the input frequency. Neat, huh? Now, in the real world, the registers are bigger, perhaps 16 bits wide. So overflow occurs when the maximum unsigned value of a 16-bit register is exceeded, and that is when the sum is greater than or equal to 65,536. And that means you can divide by utterly ridiculous values like 25 and 23,925, 65,536. The point is, you can generate frequencies that are spot-on value with just a single crystal oscillator, and that's the point of a frequency synthesizer. So that's the story. You now know all about frequency synthesizers from top to bottom. Just start with a good stable frequency source, and you can synthesize any frequency using a phase lock loop and a fractional in divider.
Thank you for watching this video. For more information on this topic, please go to our website at www.maximintegrated.com under Products, Communications, Wireless RF, PLLs, and VCOs. We hope you enjoyed this video and see you again in another educational video of Maxim Integrated.